Hi, my name is Arushi, and this is my Physics 2212 Lab 6 Faraday's Law Lab Report. So, in the introduction, we're going to talk about the purpose of the lab, and the purpose of this lab was to explore Faraday's law by observing and computing the behavior of the magnet dropping down the tube and forming a field that is induced. The models that were used is the real-life magnet and tube interaction, which was like the in real-life model, and then we have the computational model that we coded on GlowScript. The results were that the predicted time was 0.91 seconds, and the average experimental time was 1.098 seconds. So the physics principles involved were Faraday's law. Faraday's law states that the changing magnetic flux through a loop induces electromotive force. The faster the flux changes, the stronger the induced voltage and resulting current. And here's kind of the equation. Then we have the magnetic field in a loop. A current carrying loop creates a magnetic field that circulates around the wire and passes through the area. The strength of this field depends on the current and the geometry of the loop. And then the third principle was change of flux, which is the magnetic flux changes when either the magnetic field strength, the area of the loop, or the orientation of the loop relative to the field is changing. This change in the flux is what triggers the induced EMF. So all three of these principles are related, and here are like three equations to help kind of visualize them and are big parts of this lab. The experimental setup. So the steps in the setup were that the first one was to use the magnetometer app to mark the north pole of the bar magnet. The second was to hold the tube of aluminum and record it using a camera. Third was to record yourself dropping the bar magnet through the tube vertically. And then the fourth one was to find the time step of the magnet entering and exiting the tube to record the time and find the difference between the different times. And to find the difference, you need to repeat the procedure 5 times to get the average fall time of the bar magnet as it falls through the tube. So here's the observed model. We have our trials. So the first trial was 1.11 seconds. Second was 1.09 seconds. Third, 1.04. Fourth, 1.15. Fifth, 1.10. The average time was 1.098 if you add them up and divide them. And basically what this shows is that the magnet slows down its velocity as it enters the tube. And here's a picture from one of our videos. Obviously we have 5 different videos. I couldn't really fit them in. So here's a picture of us in lab dropping the bar magnet through the tube to get the times. And here's the computational model. So the time in the tube was 1.06 seconds, and it took 0.91 seconds to fall through the tube. So this is like our final results that happened after you see your code. Here you could see the time versus velocity graph, and you could see kind of the relationship between the two in this graph here. And then here is also the visual representation of the computational model. And then here we're going to talk about the code. So I split up the code into 2 different parts, but basically in the code, to really get the idea of it, I first initialized the physical constants and model the aluminum tube as a stack of conductive rings and the magnet as a point dipole. Inside the main simulation loop, I calculate the changing magnetic flux for each ring to determine the induced current and the resulting upward magnetic force on the falling magnet. And this is all in the GlowScript code, so this is kind of the beginning. Here's step 2, and then here is more of the code if you want to follow along with it. I try to include the more important parts, but as I explained before, this is what's happening. Some possible sources of error are that the error in the data collection and results provided aren't accurate, so there's just an error in the data in general. We didn't account for the air friction or other forms of friction, and that the tube was not upheld properly, like vertically, and it wasn't perfect. So some of the discussion questions are, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, by reducing the resistivity of the conductor to as close to 0 as possible, it will have a greater magnetic force, and this will make the magnet fall slower through the tube. And then what if the holes or slot were cut into the tube? How would that affect the ring currents in my model? By cutting the hole into tubing, by cutting holes into the tube really in general, it would result in the current reducing, which would make the magnet fall faster, and you could kind of see the relationship. Thank you.